Imagine you're building a computer program that can recognize handwritten digits. You show it a messy, scribbled 3, and somehow, it needs to confidently say, "That's a 3. We've seen how neural networks can make these predictions. They take an image, process it through layers of interconnected nodes, and output probabilities for each digit. But how does the network learn to do this? How does it get better at distinguishing a 3 from an 8? In our previous video, we built up the intuition for how a neural network takes an input, like our handwritten 3, and performs a forward pass to generate an output prediction. We understood the roles of weights and biases in transforming information. But that's only half the story. A network that just predicts isn't very useful if its predictions are wrong. The real magic, the true intelligence, comes from its ability to learn from its mistakes. Today, we're going to unravel the core algorithm that makes this learning possible: backpropagation. So, why do we need to learn? Because when we first initialize a neural network, its weights and biases are essentially random. It's like asking a toddler to identify a 3 for the first time; they'll just guess. The network makes a prediction, and we compare it to the correct answer. For our 3, the correct output should be a high probability for the 3 output node, and low for all others. The difference between what the network predicted and what it should have predicted is what we call the error or loss. Our goal is to minimize this error. To do that, we need to adjust the network's internal parameters, its weights and biases. Think of them as the network's adjustable knobs. If the prediction is wrong, we need to turn these knobs in just the right way to make the error smaller next time. But here's the challenge: a typical neural network can have thousands, even millions, of these weights and biases. How do we know which knob to turn, and by how much, to reduce the error most effectively? We can't just randomly tweak them; that would take forever. We need a systematic way to find the direction of steepest descent in our error. Imagine you're blindfolded on a mountain, trying to find your way down to the valley floor. You'd feel the slope around you and take a step in the steepest downward direction. This steepest downward direction is precisely what the gradient tells us. In mathematics, the gradient is a vector that points in the direction of the greatest rate of increase of a function. For us, we want to go down the error, so we'll move in the opposite direction of the gradient. Now, how do we calculate this gradient for each individual weight in our complex network? This is where the genius of backpropagation comes in. It uses a fundamental calculus concept called the chain rule. Think of it as assigning blame. If the final prediction for our 3 is wrong, which weights are most responsible? The weights connecting to the output layer? Or the ones further back in the hidden layers? Backpropagation starts at the output layer and works backward. First, it calculates how much each weight directly connected to the output layer contributed to the error. This is relatively straightforward, as these weights directly influence the final output. For each output node, we calculate its local gradient, how sensitive its output is to changes in its input, considering its activation function. This tells us how much a small change here would affect the final error. Now for the clever part, propagating this blame backward. The error signal from the output layer isn't just used to update the last layer's weights. It's also passed back through those weights to the previous hidden layer. This is the chain rule in action. The error at a hidden node is a combination of the errors it contributed to all the subsequent nodes it connects to. We essentially multiply the error signal coming from the next layer by the weight of the connection it traveled through. Once we have this propagated error for a hidden node, we can then calculate the gradient for the weights connecting to that hidden node from the layer before it. The full gradient for any weight is essentially the error signal coming back, multiplied by the local gradient of the node it connects to, multiplied by the input that fed into that weight. Once we've calculated the gradient for every single weight and bias in the network, we can finally update them. The update rule is simple: new weight equals old weight, learning rate times gradient. The learning rate is a crucial hyperparameter. It controls how big of a step we take down the error landscape. A small learning rate means slow, cautious steps. A large learning rate means bigger, potentially unstable jumps. This entire process, forward pass, calculate error, backward pass, backpropagation, update weights, constitutes one training iteration. We repeat this thousands, even millions, of times, showing the network many examples of handwritten digits. With each iteration, the weights and biases are subtly adjusted, and the network gets better and better at recognizing our 3. Let's put it all together. We start with our handwritten 3 as input. It goes through the network in a forward pass to produce a prediction. We compare this prediction to the true label to calculate the error. Then, the magic of backpropagation begins. The error signal flows backward through the network, layer by layer, using the chain rule to calculate the gradient for every single weight and bias. Finally, using these gradients and our learning rate, we update all the weights and biases, making tiny adjustments that nudge the network towards better predictions. This cycle repeats, refining the network's understanding of what a 3 truly looks like. Imagine trying to do this by hand. For every single pixel in our 3, for every connection, for every layer, calculating how a tiny change would affect the final error. It would be an impossible task. Backpropagation provides an elegant, efficient algorithm to solve this incredibly complex blame assignment problem. It's how a simple collection of mathematical operations, when repeated millions of times, can learn to recognize patterns, understand language, and even generate creative content. Backpropagation is the engine of modern AI. So, let's recap what we've learned about how neural networks actually learn. First, neural networks learn by minimizing their error or loss, which is the difference between their prediction and the correct answer. Second, they use the gradient to find the direction of steepest descent in this error landscape, telling them how to adjust their weights and biases. And third, backpropagation is the algorithm that efficiently calculates these gradients by propagating the error signal backward through the network using the chain rule. In our next video, we'll dive deeper into different types of activation functions, explore various optimization algorithms that refine how we use these gradients, and discuss techniques to prevent overfitting. If this kind of deep understanding of AI foundations is valuable to you, consider subscribing to the channel. Your support helps us create more content like this. One more thing for the curious: while backpropagation is incredibly powerful, it's not without its challenges. As networks get very deep, a problem